Hello friends, welcome to this second video lecture on proving techniques. Now in this lecture, we are going to cover the concept of proving techniques with the help of the topic contradiction. So now let's understand briefly what is proving techniques. So now proving techniques is something that is going to help us prove that whatever we do, okay, or whatever function we run, okay, the output that is coming out of it, it's going to be true. So this is a technique which is just going to verify our work. So let's get started. Now, what happens in proof of contradiction? So let us say that proof of contradiction is like our life, okay, that we try something new, okay, even if we are not sure about it, we try it, and then if we fail in that, okay, then we come to a conclusion that whatever we tried was not right, and let's try the other way around now, okay. So similarly over here, contradiction is an argument of the form, okay, there is a claim, and finally this claim, if it leads to contradiction, okay, then we have to prove otherwise. So let's understand that. So now you can see that I put a negation to the claim. That means if we have any kind of claim, that has to be proven. So how to get started? So there are some steps for proof of contradiction. Okay, if we get a claim, let it be any claim, we'll assume that the negation of that claim is true. That the negation of the claim is true. Then using the negation of the claim, I'll try to proceed ahead. Okay, I'll try to derive things. Okay, I'll try to prove something. And as I keep on proceeding, I might lead to some absurd result or some absurd outcome wherein like just cat equal to dog. Okay, so in this case, you can see that's completely impossible. So obviously, if I'm leading to something which is contradicting, we can say that whatever we started with was wrong. Okay, the assumption was wrong. So what was the assumption? That we are starting with the negation of that claim. So if the negation of the claim is false, in the third step, we can see that if negation is proved to be false, therefore we can say that the original claim was true. So let's proceed. Now, let's understand this with the help of an example. Now, in this statement, we have that the sum of any two consecutive number is odd. Now, this is a claim that sum of any two consecutive number is odd, and we know that it's odd. Okay, but how to go about proving it? Okay, so to verify the correctness of it, let's get started by saying that let k be some integer. Okay, so let's have some definitions first. Definition one: an integer n is even if and only if some k such that n equal to 2 times of k. So obviously, if I'm proving that something is even, it has to be some multiple of 2. And k is an integer. Okay, so multiplication of integer with 2 will result into an even number. Now definition 2, an integer n is odd if and only if some k such that n is equal to 2k plus 1. So you can just see I have just added 1 for it to be odd. The definition 3, two integers a plus b are consecutive if and only if b is equal to a plus 1. Okay, obviously for it has to be consecutive, I just need to add 1 to one number and we get the other number. So now I've just given some notations below. You can just check them out. If I write IFF, it means if and only if. It's there's a backward E. It means it's there exists. And you can see the next one. Okay, it's the symbol for belongs to. So now let's start with the proving by contradiction. So let's understand the fact first. Now, what is the fact in consideration? That a and b are two consecutive integers. So let's start with the assumption. Okay. So the thing was the claim has to be a plus b is odd as a and b are consecutive numbers, integers. Now the assumption we have to start with something otherwise than this. So we'll say that the addition of a and b is not odd. Okay, so I will negate the claim first. So we are negating that a plus b is not an odd integer. Now, if a plus b is not an odd integer, okay, so you need to understand that there could be no integer k such that a plus b equal to 2k plus 1. Because for a number to be odd, it has to satisfy the formula 2k plus 1. So if a plus b is not odd, it is not going, there's going to be no k which is going to satisfy the odd formula which is 2k plus 1. But just look at the next step. We say that a plus b equal to a plus 1. Why? Because as per the definition that we saw in the last slide, we knew that if there are two consecutive numbers, right, then b should be equal to a plus 1. So I'm just replacing b as a plus 1, and if I sort this particular formula, it comes out to be 2a plus 1. Now obviously a is an integer. If a is an integer, and in the formula for a number to be odd, even k is an integer, then obviously we can see that in one, we just concluded by a assumption that a plus b is not equal to 2k plus 1. So 1 and 2 are contradicting each other, which can lead to say that our assumption is wrong. Hence, we can say that our original claim that the sum of any two consecutive number is odd is correct. So this is how we prove the prove the correctness by proof of contradiction. Let's understand with another example. Okay, so now in this example, let's say that root 2 is an irrational number. Now that is a claim again. Now how to go about proving it? So let's start by assuming the negation of the claim is true. So it means that root 2 is a rational number. So now, if root 2 is a rational number, what is a rational number? A rational number is something which has some fixed decimal values, okay, fixed decimal numbers. Because in irrational numbers, we have decimals which are non-terminating. They keep going on and on and on, right? So in this case, we need it to stop. We need it to be like a fixed value after the decimal. So we can say that if root 2 is a rational number, okay, it will be what? A divided by B, where A and P are what? Co-prime numbers. Now what are co-prime numbers? Co-prime numbers are the numbers which doesn't have any common factor. Okay, so let's take an example. Let's say that I'm saying A is 20 and B is 10. Now 20 and 10, it has a very basic common factor of 2. So if I just divide them, it will 20 will become 10 and 10 will become 5, right? So 10 by 5. Now 10 by 5, okay, do you see any particular any particular factor in this? No, we can't see any particular factor in this. So we can say the number 10 and number 5 is co-prime numbers, are like co-prime numbers. So that means we are reducing two numbers to its very basic form, wherein they don't have any kind of factors between them. Those are what? Co-prime numbers. So if you have two co-prime numbers, if I do 5 divided by 10, what do I get? If I do just 5 divided by 10, I get 0.5. Right? So if I get 0.5, so obviously after the decimal, I just have one digit, that is 5. So it means that it is terminating. Okay, and it's not going on and on. So this is what we are trying to prove, that A and B are co-prime numbers, which is so root 2, if it has to be rational, it has to end with some definitive numbers after the decimal. So let's see whether it works out. So that is our claim. Now, so proceeding ahead, we can see that we'll just square both sides. Okay, so root 2 becomes after squaring becomes 2, and on the right hand side we see a plus b the whole square becomes a square plus b square. Now finally, uh, it is like 2b square equal to a square. Now what is b square then? B square is a square divided by 2. Now if a square is divisible by 2, then we can say that even a is divisible by 2. Okay, so you need to check it for any number, and you'll understand that if a number is divisible by 2, okay, so it's not just 2. Okay, if a number is divisible by any prime number, sorry, square of a number is divisible by any prime number, then that number is also divisible by that prime number. That is one of the other formulae that we use. Okay, so in this case we can say that uh, 2 into some integer c is equal to a, as a is divisible by 2. Okay, so the factor that we would get is c. So 2 into c equal to a. Now substituting this particular thing, 2 into c, which is equal to a, in equation 1. So in equation 1, what was equation 1? It was 2b square equal to a. So in a square. Now instead of a square, we are having 2c square. Now again, you see, if I solve it, it comes like b square equal to 2c square. So if b square is divisible by 2, then again we can say that b is divisible by 2. As by some mathematical formula, it has been proven that like if a particular number square is divisible by the any particular prime number, then even that number is divisible by that prime number. So using this technique, we can see that both A and B are having one common factor, that is 2. But is it how we started it? No. We said that A and B are supposed to be co-prime numbers. If they are supposed to be co-prime numbers, then they shouldn't have any common factor, right? We said that co-prime numbers are the numbers, okay, which are already brought to their reduced form. Okay, that means they don't have any common factor. But after solving this, we see that even A is divisible by 2, okay, and even B later is divisible by 2. So kind of they both have a common factor of 2, which is contradicting our claim, right? So our claim was there shouldn't be any common factors. Here we can see common factors, so we can clearly state that our claim was wrong. So again, I would like to reiterate the statements. Okay, so what was it? So we assume that there's some claim, okay, and we say that the negation of the claim is true, and then we start processing the claim, okay, with the negation. So negation of the claim, when we proceed, we derive to a contradiction, okay, and some that contradiction is something that is impossible, okay, that we can't go ahead with it. So hence we prove that the assumption is wrong. So as the negation of the claim is proved to be false, we say that the original claim is true. So that is it. I hope that you have understood the concept of contradiction. Thank you so much. Enjoy algorithms.